All right, let's jump right in. Today, we're taking a look at a really fascinating connection. We're going to link the extreme, mind-bending forces of astrophysics directly to the physical spaces we live and work in every single day. If you love understanding the hidden structures governing our world, you're in the exact right place for this explainer. We're going to explore how the invisible, fundamental rules of the cosmos actually translate into the physical blueprints of human architecture. Think about this for a second. What on earth does a falling object plummeting through space have in common with the architectural blueprint of a modern skyscraper? At first glance, literally nothing, right? One is this dynamic physical event controlled by gravity, the other is a static, human-designed structure. But as we're going to see, the physical forces of nature don't just push and pull on objects. They actually dictate the mathematical frameworks we use to build our most stunning structural environments.
Okay, to make sense of this, we first need to look at two fundamental physics curves. First up is the brachistron. That's the path of fastest descent. It's the track an object should take to get from point A to point B as quickly as possible. And then there's the tautochron, which is the path of equal time. This means no matter where you drop an object on this specific curve, it'll always take the exact same amount of time to reach the bottom. Now, under normal uniform gravity, like what we experience here near the Earth's surface, these two paths are perfectly aligned. They harmonize elegantly into a single curve called a cycloid. But what happens when the rules of gravity suddenly change?
Let's dive right into this because this is where it gets wild. Imagine shifting from a uniform gravity field to a planetary scale, one with a massive, changing density profile. Gravity starts behaving very differently. As it spikes violently near a hyperdense core, it obeys an inverse square law, or it might even spike into a power law distribution. Because of these intense shifts in the density profile, those two perfectly harmonious paths violently split and warp. The brachistron, wanting to steal kinetic energy as fast as possible, just nosedives, warping into a steep, sharp plunge straight toward the core. And the tautochron? Needing to maintain equal time despite that massive gravity spike, it flattens out radically to stop the object from accelerating too quickly. That perfect harmony is completely shattered.
And you know, this extreme divergence presents a massive mathematical headache as gravity scales up so aggressively into this power law spike. Acting basically like a deeply compressed mass or information stack, classical calculus just completely falls apart. The math simply cannot handle the center of this gravity profile because it creates an infinite point singularity. The trajectories become incredibly densely packed and recursive, and the mathematical area just vanishes rapidly with every step. We're essentially careening toward continuous mathematical gunk.
To put a physical analogy to this abstract math, think of that core singularity as a zero-dimensional ghost point. It's basically an infinite chaotic pit. Any mathematical path or particle heading toward it just falls endlessly into an infinite gravitational well. If you were designing an algorithm, this is exactly where it would fall into Zeno's infinite division, constantly having the distance forever but never actually arriving, and ultimately it crashes. It becomes that continuous mathematical gunk that just never resolves. So how on earth do we solve this so we can actually use this geometry for design and architecture?
Well, the answer lies in an incredibly elegant mathematical trick called normalization. In classical math, you're constantly trying to balance independent variables like the A, B, and C sides of a right triangle. But through base scale geometry, we can take what we call the transverse constant, which is effectively the baseline foundation of our space, and set it exactly to 1. By locking in this foundational constant, so A equals 1, we reduce this entire chaotic geometric mess down to a single independent slider, the variable B. For parametric architecture, this is an absolute game changer.
But hey, we still have to deal with that infinite singularity at the center, right? This is where we introduce the concept of the quark, represented by the variable capital D. The quark physically plugs the infinite hole in our mathematical well. It replaces that zero-dimensional ghost point with a finite physical boundary, a terminal resolution floor. By replacing the infinite abyss with this finite quark boundary, D, we successfully stabilize those extreme physical and mechanical trajectories we saw earlier. Our computation doesn't crash into chaos anymore. It transitions smoothly into a bit-perfect, deterministic halting step. Which brings us to this beautifully unified base-scale equation. Just take a second to appreciate the elegance here. Capital D equals the square root of 1 plus b squared minus b, all raised to the power of n. By integrating that normalization trick we just talked about, architects can use this exact, surprisingly simple equation to calculate a building's central footprint. And they can do it directly from the number of nested fractal loops, represented here by n. No complex coordinate tracking needed. They just use this single, powerful formula. So the crucial point is how this translates to a real physical construction site.
Let's say you're an architect and you're designing a structure that recursively spirals inward exactly 4 times, meaning n equals 4. And let's say you want to ensure that exactly 25% of your central footprint remains completely open, maybe as a public courtyard or a huge atrium. You literally just set your terminal floor, your d, to 0.25. By solving for b using that single slider, the math instantly spits out the exact physical offsets your construction team needs to tape out on the ground. It perfectly balances the entire spatial envelope.
All right, let's map out how this builds our understanding of spatial harmony. We're essentially tracking a transition here. Step 1 is that high-decay power law zone, that extreme, violent plunge toward the core where mathematical area vanishes. Step 2 involves seeking a geometric diamond balance to counter that massive plunge. And finally, Step 3 is achieving what is mathematically known as the silver horizon resonance.
And man, the real magic happens at this exact mathematical resonance, the silver horizon, where lowercase d is approximately 0.414. This concept is deeply tied to the foundational work of Dr. Vera W. de Spinedel and her introduction of the metallic means family to architectural scaling systems. At this exact geometric proportion, those extreme physical and mechanical trajectories we've been tracking are perfectly stabilized. The system starts mimicking a perfect harmonic oscillator, laying the groundwork for truly self-balancing parametric architecture. At the silver horizon, a unit cell smoothly and inherently divides into its own substates without any approximation drift. It is literally the absolute ultimate state of structural and aesthetic balance.
It is genuinely mind-blowing how this connects back to the modern tools we use today. The exact same logarithm bases that describe varying gravity profiles and changing planetary density are being utilized right now, as we speak, in 3D modeling programs like Rhino and Grasshopper CAD to build our world. Because normalizing our a variable to 1 simplifies the vector math so completely, the coordinate step size of every single nested room, column, or facade panel scales perfectly. Computers can just use lightweight Python or JavaScript to instantly render entire modular city blocks under one unified coordinate space. That is the raw power of these equations at work.
And visionary designers have actually been leveraging these concepts to move past the rigid limitations of traditional Euclidean geometry. Sometimes they did it intuitively in the past, but now it's highly computational. We can see these exact applications of fractal recursive scaling coming to life in the stunning, nested equilateral triangles of Frank Lloyd Wright's Palmer House, mapped out across 7 different scales. We see it in the striking fractal panel facades of Story Hall in Melbourne and those complex aperiodic tessellations of Federation Square. It's this precise math that allows us to build environments that are highly complex, yet incredibly sustainable, human-centric, and uniquely biophilic.
And this brilliantly illustrates the whole concept coming together. You can start with a simple, foundational base tessellation, but by applying that base scale math and the silver horizon resonance we've explored, the space just recursively expands. These nested structural loops resolve complex spaces completely seamlessly. You don't get any awkward gaps or forced angles. It all exists within a single, unified coordinate space that perfectly stabilizes those physical and mechanical trajectories into breathtaking, self-balancing parametric architecture. Which leaves us with a pretty profound question to wrap up this explainer. After seeing how the pathways of falling objects under massive gravity spikes share the precise mathematical blueprints required to render a fractal skyscraper, we really have to ask, are our buildings merely aesthetic choices made by human designers, or are they in fact physical manifestations of universal gravity equations, perfectly corking the infinite to create balanced space? It completely reframes how you look at the world built around us, doesn't it? I hope this explainer has given you a powerful new lens through which to view both the cosmos and your own city skyline. Keep looking closely, keep questioning, and keep learning.